Hello everyone, welcome to lecture 4. In this one we're going to talk a little bit more about semiconductors, and we want to look at the idea of electrons and holes. So first of all, let's talk about examples of semiconductors. We learned in the previous lecture that semiconductors have this narrow energy gap between the two bands. So they still work as insulators, but they're not as good as insulators as other materials. And we talked about at the end how with enough energy that gap can be overcome, which is something that is true of all insulators, really. So in this case, let's begin by talking about some examples of semiconductors. So the two main ones that are sort of natural semiconductors are silicon and germanium. And of the two, we really care about silicon most of all. We'll talk a little bit about germanium in a future lecture, but silicon is really the one that we care about the most. It's a very common element, so it's very often used. And silicon is important because it acts as a semiconductor, and in its valence shell, it has its nucleus and it has 4 electrons on the outside. And again, we talked about this in a previous lecture. It tends to create this crystal structure like so, where it links up its 4 electrons. So everything around it also links up with an electron. We call that covalent bonding. However, we've also talked about in semiconductors that this energy gap can be overcome. So in a normal situation, there's not going to be any flow of electrons, but it is possible. And when it does happen, like if there's enough heat, for example, sometimes these covalent bonds can be broken, and instead of linking up, an electron will go into the conduction band, and it will move to another atom, and it will leave behind a hole. And now things start to get interesting, because now there's a hole. So things have been knocked free because that energy gap has been overcome. So now there's a hole and there's a place where another electron might fall. So now we have an extra electron that is looking for a home, and we have a hole where something can accept an electron. And we end up in this situation where it's not quite the perfect crystal structure that we originally had. We have a series of holes and extra electrons, and that is what starts to allow this to have a little bit of conductivity. So that's really it. And the really interesting thing about this is we're basically, like, a hole is a place where an electron can fall into. It's a kind of a gap, and these extra free floating electrons are additional negative charges. So these holes that happen in silicon, we give a positive charge to. So it's obviously not a positive charge like a proton is a positive charge, but because it's missing an electron, the proton now outweighs the electrons, so that hole represents a positive charge. So that's just kind of a weird thing that happens. And when we look at the flow of electricity and the flow of energy in a semiconductor, we can either look at the movement of negative charges, which are electrons, or we can look at the movement of holes, which represent a flow of positive charge, because holes will also move about, because as this hole gets filled, it's taking an electron from somewhere else, which creates another hole. So that is really deep down what is happening inside of a silicon semiconductor. And in the next lecture, we're going to look at how different doping mechanisms can be used to kind of take advantage of this electron and hole relationship. So that is what you'll see in the next video.